4.2 experiments. So some vocabulary in this section, an observational study versus experiment. So with an observational study, okay, that all that is we just observe individuals and we measure any variables of interest. But the important thing is we do not attempt to influence any response. So we're just watching people. Okay, we're just watching people. Whereas if we do an experiment, we deliberately impose some treatment. So experiments, a lot of times they involve like medicine, when we give one group a sugar pill called a placebo to one group, but we give the pill with the actual medicine to another group. There we're deliberately imposing some treatment on an individual. And then we measure their, for instance, drop in cholesterol. Okay, so the difference between the two, experiment imposes a treatment, an observational study does not. That's the difference. All right, so we also have these things called lurking variables. So we're measuring something, we're imposing some treatment in an experiment. There might be other things causing the results. Okay, so if we have a variable called a lurking variable, that is not the explanatory or the response variable, but influences the response variable. That's called a lurking variable. Okay, it's called a lurking variable. And this idea of lurking variables has the effect of that is called confounding. Okay, so confounding occurs when two variables are associated in such a way that their effects on a response variable cannot be distinguished from each other. All right, so you might have two variables causing something, but we don't know which one is more to do with the response variable. All right, the specific condition applied to individuals is called a treatment. If an experiment has several explanatory variables or factors, a treatment is a combination of specific levels of these variables. And lastly, experimental units are the smallest collection of individuals to which treatments are applied. When units are humans, they're called subjects. So let's do a practice problem in here. Okay. So here it says a study published in the New England Journal of Medicine back in 2010 compared two medicines to treat head lice. An oral medication called ivermectin and a topical lotion containing malathion. I don't know if that's how you say it. Researchers studied 812 people in 376 households in 7 areas around the world. Of the 185 households randomly assigned to ivermectin, 171 were free from head lice after 2 weeks, compared with only 151 of the 191 households randomly assigned to malathion. Identify the experimental units. Okay. So they're giving us we kind of have to read this, and we're trying to identify these things. Okay, we're trying to identify these things. So experimental units. You might first think that the experimental units are the people, but the results that they give us have to do with households. Okay, so the experimental units are the households. There's 376 households. All right, because if you read what experimental units are, the smallest collection of individuals to which treatments are applied. So we're applying these treatments to the household. So everybody in one of the households is going to get one of these two drugs. Okay. So what are the explanatory variables? Okay, what are the explanatory variables? Okay, well, the explanatory variable is the medicine that was given. Okay, so the medicine that was given, okay, and we have two of them in this case. Okay, there's two factors here. there's the ivermectin, and the malathion. So those are the two factors. Okay, what are we measuring? The response variable is what we're measuring. All right, so what we're measuring is head lice. All right, so the response variable is having head lice or not having. So it's having or not having head lice. And the treatment are just the two medications. Okay. All right, so there's two medications. Let's look at example 2. Does adding fertilizer affect the productivity of tomato plants? How about the amount of water? So we're kind of looking at different things here. So we have fertilizer, okay? Does that affect the productivity of tomato plants? Like whether they grow or how much they grow? And water, does how much water we put into the ground affect the productivity of the tomato plants? To answer these questions, a gardener plants 24 similar tomato plants in identical pots in his greenhouse. He will add fertilizer to the soil in half of the pots. Also, he will water 8 of the plants with half a gallon of water per day, 8 of the plants with 1 gallon of water per day, and the remaining 8 plants with 1.5 gallons of water per day. At the end of 3 months, he will record the total weight of tomatoes produced on each plant. Identify the, okay, so we got to identify all that thing. On this one, it might make sense to make a graphic of the situation. All right, so we have 24 plants. It says that he will add fertilizer to the soil in half of the pots. So you're going to have 12 with fertilizer, and then you're going to have 12 without fertilizer. Okay. And it also tells us that he will water 8 of the plants with half a gallon of water per day. So in 4 of them, I'm going to split this up evenly. So in 4 of those over here, and in 4 of these over here, all right, they get a half gallon of water. All right. So I have the 8, 4 and 4 make 8. All right. And then it says he'll water or 8 of the plants with 1 gallon of water. So we need to have 8 there. So I'm going to put 4 over here that also get fertilizer, and 4 over here that don't get fertilizer. Right. And then in the remaining 8, we have 1.5 gallons. All right, so now I'm getting messier as I go down the page here. So I have 24 plants. I have 12 over here on the fertilizer side, 12 over here and without fertilizer side. 4 of them get a half gallon, 4 of them get a half gallon. Okay, 4 of them get a gallon, 4 of them get a gallon. 4 of them get 1.5 gallons, 4 of them get 1.5 gallons. All right. So the experimental units here, okay, what are the experimental units? Well, they're the 24 tomato plants. Now, what's affecting their growth? Okay, what is explaining their growth? Well, fertilizer could affect it. So fertilizer is one explanatory variable, or one factor, and the other factor is the water. So the amount of water, all right, and we can say presence or absence of fertilizer. Well, what's being measured? What's being measured? The size or the growth of the tomato plant. All right. And what are the treatments? Okay, so over here, looking over here at the treatments, there's 6 basically treatments. Okay, we have basically 2 factors, and you have 3. Okay, the factors are the fertilizer. The factors are the presence or absence of fertilizer and the amount of water. Okay, and then there, for each of those, okay, there's 3 different criteria. Okay, so there's basically going to be 6. There's going to be 6 treatments. Okay, there's 2 factors times 3 to get treated. There's 6 treatments, because if you look here, there's 6 boxes. 1, 2, 3, 4, 5, 6. Okay, so one treatment is fertilizer with a ½ gallon of water. That's one treatment. The other is no fertilizer and a ½ gallon. Then we have fertilizer gallon, fertilizer 1 gallon, and then no fertilizer 1 gallon. And I'll put the other 2 over here, so 5 and 6. All right. So the last 2 are fertilizer with 1.5 gallons of water and no fertilizer with 1.5 gallons. Okay. So over here, when we get to levels, if we take the 2 factors, all right, times the 3 levels, all right, so of this factor, well, it's not really 2 factors. Of the first factor, fertilizer, we only have 2 options. We have 2 levels. So you have levels of fertilizer. You have fertilizer, no fertilizer. So those 2, that has 2 options for fertilizer. And you have 3 options for the amount of water. So you take 2 times 3. It's a basic multiplication principle. Okay, so there should be 6 treatments. All right, so each pot will get one of, and in each of these 6 treatments, there's 4 plants in each treatment. All right, so there's 6 treatments here, and each pot will fit into one of those. Each pot fits into one of those treatments, and for each treatment, there happens to be 4 pots, or 4 tomato plants in there. All right, next page. It says, how to experiment badly. All right, let's read this example. Many students regularly consume caffeine to help them stay alert. Thus, it seems plausible, or could be explainable, that taking caffeine might increase an individual's pulse rate. Is this true? Here's an initial plan for the experiment. Measure the initial pulse rate. Okay. Give each student some caffeine. Wait for a specified time, measure their final pulse rates, and compare final and initial rates. What are some problems with this plan? And what lurking variables should we be aware of? Well, the problem with this plan, you can probably think to yourself, there are many variables that can increase pulse rate. Okay. There are many variables that can increase pulse rate. Thinking that just amount of caffeine contributes. All right. So I'm thinking a lot of things can increase my pulse rate. Thinking that just amount of caffeine contributes is, well, what's the right way to say this? I'm not erase that. All right, let's just stay with that first sentence. There are many variables that can increase pulse rate. More than just caffeine affects pulse rate. What lurking variables, what other things can we think of can cause increases to pulse rate besides caffeine? Well, all right, amount of stress. All right, the amount of stress, physical activity. All right, if we just measure someone that just got done sprinting, their pulse rate's going to be really high, and after a certain amount of time, it's going to drop down. Okay, so physical activity can affect pulse rate. Amount of sleep can affect pulse rate. Just your general health and well-being. All right, so if you're a pretty healthy individual, okay, you're going to have a lower starting pulse rate than someone that's not in good health. Sickness, if you're sick, that will affect your pulse rate. So all of these things can contribute to your pulse rate. I mean, caffeine can as well, but we're not controlling for these things. So the plan doesn't have any type of control that will keep all of these things level. All right. So if you just looked at people that, if you kind of narrow down your selection to people that have about an equal amount of stress, that have the same physical activity level, that get about the same amount of sleep, that are pretty healthy, if they're all healthy in your experiment, and if they're all, if none of them are sick, you're controlling for some of these things, but there's other things that we probably didn't even list that we can think of. So they're lurking variables. They can cause confounding with our results. All right. So that's kind of how you experiment badly. Okay, you need to, the best way, if you want to think something might influence something else, you need to control for these other things. Okay, you need to take them out of play. So how to experiment well is the randomized comparative experiment. All right. So here's a couple ways that you can do that. All right. If you randomly assign people to groups, that's one definite thing you have to do in an experiment. That means that experimental units, or people in most cases, are assigned to treatments at random. So let's say that you have like 100 people, for instance. Okay, at random, you need to put 50 into your experimental group, and you need to put 50 into your control group. But you have to pick these people at random. So after you have your 100 people that are going to be part of the experiment, 50 have to be randomly assigned to get some medication, and 50 have to be randomly assigned to get the other medication or the placebo or control. All right. That's called random assignment. Random assignment is crucial in experiments. All right. Now, in a completely randomized design, the treatments are assigned to all the experimental units completely by chance. All right. So we'll talk about other types of design like block design and things like that, but that's kind of what I gave you up here. All right, completely randomized. So I flip a coin. All right, and if I flip a coin, if for each person. If it comes up heads, they get one drug. If it comes up tails, they get the other. All right. So let's look at example 4. Many utility companies have introduced programs to encourage energy conservation among their customers. An electric company considers placing small digital displays in households to show current electricity use and what the cost would be if this use continued for a month. Will the displays reduce electricity use? One cheaper approach is to give customers a chart and information about monitoring their use from their outside meter. Would this method work almost as well? So they're talking about one method here. All right, I'm just going to underline it. So here was the second method. All right, the company decides to conduct an experiment to compare these two approaches. So the display method, which would be very expensive for the company to do, or a chart, with a control group of customers who receive information about energy consumption, but no help in monitoring their electricity use. So that's kind of a control group. So we actually have 3 groups here. It says, outline a completely randomized design involving 60 single-family residences in the same city who are willing to participate in such an experiment. Write a few sentences describing how you would implement your design. Okay, so we have 60 families. All right, and we want completely randomized, but we want about the same number in each group. All right, so we want 20 to have the first method. We want 20 to get the second method. And we want 20 to be part of our control. Okay, or the third method. All right, so they just want me to outline this. So here's how I'm going to do it. I'm going to put all 60 family names in a hat and shake it up. All right. I'm going to draw 20 names without replacement. Okay. I'm going to draw 20 names without replacement and provide the digital display to those families. Then I'm going to draw 20 remaining family names without replacement. I should say draw 20 additional remaining names without replacement from the hat, and provide those families with the chart. Okay. The last 20 families whose names were not drawn will receive info but no help in monitoring. Okay, so that's my design. That's my experimental design right there. I'm telling the reader, the grader, how am I going to break these 60 families up so I can randomly put 20 people in each method. And I just did that in a few sentences. All right. It says, describe how you would carry out the random assignment. provide enough detail that a classmate could implement your procedure. Okay, so I talked about how I'm going to put these families into the three groups. Okay, but I need to talk about, well, I guess I kind of did that. I already, this is how I'm going to carry out the random assignment. All right. All right, so this is partly A and B. But I could also say before placing, all right, before placing the families into groups, we would measure each family's electricity usage then after a set amount of time, we would measure the amount of reduction. And electricity use. Okay. So the last question here, it says, what is the purpose of the control group? Why do we have to have this control group? Because we want to see, in any type of experiments, and important to have a control, because these people know that they're participating in an experiment. They might be subconsciously wanting to reduce their electricity output because they know they're in an experiment. There's some sort of psychological effect going on. So like if the control group, the control group knows they're in an experiment as well, we would not expect this particular group to go down as much as these two because they're getting extra tools and extra information. All right. But if this group naturally just goes down by 5 because they know they're taking part in this experiment, then these two should be more than 5. That would give us confidence that these methods are more effective than getting nothing. Okay, so the purpose of the control group is for means of comparison. Okay, so like if this was a medical study, we would give the control group a placebo. We'd give them a sugar pill. Because some people who think they're getting medication, like if they're getting a sugar pill but they don't know it's just a sugar pill, if they think it's real medication, some of them will improve just because their outlook has changed. They think they're being treated for something, and their heart rates can go down if it's or their blood pressure might just go down because they think they're taking a drug. So we use control groups for means of comparison and to reduce what we call this thing called the placebo effect. All right. Like if we didn't have a control and this first group went down by 10 and this group went down by 5, then we would think that both methods are effective. But what about if the control group also went down by 5? Then we can't say the second method is any more effective than doing nothing. People in experiments tend to change their behavior just because they're in an experiment. So that's why we need a control group. So whenever you design an experiment, you want to make sure you're following the 3 basic principles. Okay, and the 3 basic principles of experimental design are control, random assignment, and replication. All right. So we're trying to, this doesn't mean have a control group all the time. It's not always necessary, but we want to minimize the effect of lurking variables that we can think might affect our results. Okay. So going back to that first example up here from the previous page, All of these things, these are just 5 things I thought of that can affect pulse rate. We would have to control for these. We would have to make sure everyone participating had about equal amounts of these things. At least that way, we can say with more confidence that caffeine is affecting people if we control for these things. So we have to control for lurking variables. Okay, that's one principle. Okay? And you still might not get all the lurking variables. All right. Random assignment. All right. So we're going to randomly assign people to multiple groups, and we want each group to be roughly equivalent. Okay, you probably want some men, some women. You probably want, you know, a fair number of old people and young people. Just depending on the experiment, you might have some sort of different races. So you want different races in each group. We want each group to be as alike as possible in some way. That way we can draw a comparison between the groups. Okay, if you have men in one group, if you have all men in one group and all women in the other group, then each group is not equivalent if you're measuring something, because they might have higher cholesterol to begin with than women. So if you're measuring reduction in cholesterol between 2 groups, if the groups are roughly equivalent to start with, then it's going to be harder to compare. So we randomly place people into several groups so the groups look overall similar to each other, which means like group 1 would look about the same as group 2. Their mean ages are about the same. They have roughly equal numbers of different genders, different races, and a whole bunch of other things that you can think of. And the last principle of experimental design is replication. So this doesn't mean replicate the experiment. What this means is that you have enough people in each group to be able to draw conclusions. Okay. So for example, if you had an experiment, but you only had one person in the first group and one person in the second group, all right, and let's say they're both middle-aged men, all right, and you give this one guy, a medication for something, and you give this guy a placebo for something. Well, maybe this guy's cholesterol goes way down. That got the medicine, but this person who got the placebo didn't have any change in cholesterol. Well, maybe this guy started working out. Okay, maybe that reduced his cholesterol. So one person in each group is not enough. The principle of replication says, okay, use enough experimental units in each group so that any differences can be distinguished from chance differences. If you only use one person, there's too much left to chance. But if I change this and I say, okay, let's put 50 people in each group, if one person starts working out in this group and that person's cholesterol goes way down, it'll affect the mean a little bit, but it won't affect it entirely. It will only be a slight decrease because of that. So replication means use enough people where if this goes down an average of 10, that's substantial. Okay, if this one goes down by 10 more than this one, all right, then you can say with more confidence that the drug might be influencing cholesterol level reduction. All right, we talked about this a little bit on the last page. The response to a dummy treatment is called the placebo effect. People think they're getting something, some sort of medicine, so they're in a happier mood because they think they're getting medicine, or things can go down just because psychologically they think they're being treated for something, and they think they're being treated for a malady or some sort of high cholesterol, high blood pressure, when in fact they're just getting a sugar pill, but they don't know that. All right. So when people think they're getting a drug, sometimes the effects are like getting the real drug. So that's what placebo effect is. All right. And some more vocabulary here. In a single blind experiment, all right, either the subjects or the or the individuals interacting with the subjects don't know which treatment they are receiving, one or the other. Okay, so in the case of a medical study, if I'm administering the pills to people, but the people don't know whether they're getting the real drug or the fake drug, that would be a single blind. If it's a double-blind experiment and I'm administering the drug, neither the subject nor those who interact with them, so neither the people who are getting the real and the fake drugs nor me, know which treatment a subject receives. So how does that come into play? Maybe the experimenters are hiring me to administer the drug, and on each drug they have a number on each drug. Now the experimenters know which numbers go with the real drug and which numbers go with the fake drug, but neither me nor the people getting the drugs know. Now the reason why they do this is, let's say that it was a single blind and I knew. Maybe I unconsciously told people that they were getting the placebo. Okay, like if someone said, well, I'm taking this drug, but it doesn't seem to be helping. I might say something, if I knew that they were getting the placebo, I could say, well, don't expect it to go down too much. Like, not meaning to tell them they're receiving the placebo, but I might have done it on accident. All right, so double blind is usually better when it can be arranged. So let's look at example 5. In an interesting experiment, researchers examined the effect of ultrasound on birth weight. Ultrasound is that gel that they put on women that are pregnant so they can see the baby. All right. It says pregnant women participating in the study were randomly assigned to one of two groups. The first group of women received an ultrasound, and the second group did not. When the subjects' babies were born, their birth weights were recorded. The women who received the ultrasound had heavier babies. All right. Did the experimental design, in this case, did this experiment take the placebo effect into account? Okay. All right. Did it take the placebo effect into account? The next question was the experiment double blind? Why is this important? And based your answers to 1 and 2, describe an improved design for this experiment. So let's go back to a placebo effect. Was there a dummy treatment based on what they told us up here? So basically you had two groups. One group got an ultrasound and the other group no ultrasound. One group got it, one group didn't. All right, so placebo effect would be a dummy treatment. All right, so is there any dummy treatment? Are the people that are not getting an ultrasound, are they receiving something that's like an ultrasound but it's really not? No. So there's no placebo effect here. So there's no placebo effect because there is no dummy treatment. All right, and it says, was the experiment double blind? No. All right. As a pregnant woman knows whether she's getting an ultrasound or whether she's not getting an ultrasound. It's pretty clear. If they put the gel on the stomach and turn on the ultrasound machine and they show it to the woman, then the woman knows if she's getting an ultrasound or not. All right. So this was not double blind. Not even single blind. All right. The women know, the women and the administrator or the administrator of the ultrasound know if the women are getting the ultrasound. So it says, based on your answers to 1 and 2, describe an improved design for this experiment. So here's one possible way. we can do ultrasound. One group could get an ultrasound, or I'll call it a real ultrasound, and the other could get a fake ultrasound. So what do I mean about fake ultrasound? All right, you could put like here, real ultrasound, just like normal. The woman gets the gel put on her stomach, and the administrator moves the gel around with the tool and shows the baby and all that. But over here, the fake ultrasound, you could put the gel on the woman's stomach and move the machine over it. But what you could do on the monitor, you could have a video, okay, video of another ultrasound, of another woman's ultrasound. So the women here would not know that they're watching a different ultrasound, not their own. Okay, so like here, this fake ultrasound, the women would not know that it wasn't their real babies. Okay, so this would in effect be you could make it single blind, okay, or you could make it double blind. It would be harder to make it double blind though, if the technician was really experienced, because as the technician was moving the ultrasound around the woman, the technician's probably going to know that as she moves it around that might not necessarily be that woman's baby. It would be harder to make it double blind, but you could definitely make it single blind. All right, and then you could measure the weights after this. You could measure the baby's weights of, the average weights of the women over here and the average weight, the baby weights of the women over there. Okay, so that would be a slight improvement to this design. Okay, it would be a slight improvement of this design. Right. So going on to the next part, inference for experiments. It says an observed effect so large that it would rarely occur by chance is called statistically significant. We'll get more into this as we go along. Okay. But one method to help us with control is called blocking. So a block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to the treatments. And the most clear example of blocking would be blocking by gender. Okay. And then a randomized block design, the random assignment of experimental units to treatments, is carried out separately within each block. So what do I mean by that? Let me do an example. Okay, so say you have some new drug for cholesterol, all right, but you think that the drug is going to affect men and women differently. So before you start randomly assigning people to get the drug or not, you can block by gender. So you could put men into one block and women into another block. And then you can say, of the men, some of the men are going to get the drug and some of them are going to get a placebo. And you could do the same thing down here. Of the women, some of the women are going to get the drug and some of them are going to get a placebo. All right, so if you think the drug is going to affect gender differently, then take all the men, all right, and then you're going to do random assignment of the men into these two groups. And you're going to do the same thing for women. All right, what does that allow you to do? Okay, that allows you to make comparisons within each block. So you could compare men who got the drug to men who didn't, but it also allows you to make a comparison between men and women that got the drug. So it allows you to make comparisons multiple ways. All right, so that's the idea of block. And then you could make more than one block, all right? You might have men, and then you could further block by like certain ages. Men aged 30 to 40, men aged 40 to 50, and then over 50. You could do the same thing for women. Or you could block by good health, bad health, or people that are overweight, normal weight, underweight, things like that. You can block by multiple things. Right? So a randomized block design, the random assignment here, okay, it happens within each block. So here's where the random assignment occurs for the block of men. Here's where random assignment occurs for the block of women. All right, so let's look at this one. Example 10. Anne is an avid baker who would like to compare two different chocolate chip cookie recipes, A and B. So she recruits 10 volunteer taste testers to rate each type of cookie on a scale from 1 to 5. She will make 10 of each type of cookie for a total of 20. Each cookie tray will hold only 10 cookies, so she will use 2 trays and bake them at the same time in the same oven, 1 sheet on the lower rack and 1 sheet on the upper rack. All right, part A. Explain why a randomized block design might be preferable to a completely randomized design. So if we get completely randomized, all right, so what I have is I have an upper sheet in the oven, and I have a lower sheet in the oven. All right, and I might have 20 spaces. I have 10 spaces on this cookie sheet and 10 spaces on this cookie sheet. What could happen is, I might get like, all right, I might get a lot of A's just by randomly, flipping a coin and saying, okay, I'm gonna flip a coin. If it comes up heads, we'll put A there. And if it comes up tails, we'll put B there. All right, if we do completely randomized, you could have like 7 A's on the top shelf and 3 B's. And then on the bottom shelf, you would have 7 B's and 3 A's. But the location where they are might affect how cooked they get, which might affect the taste. If you did a block design, all right, if you did block, the way that would work is you would start with your 20 cookies, all right, but you would block by location. So we would make 10 cookies go to the top shelf, all right, and 10 would go to the bottom shelf, all right. But then we could say, okay, we're going to make sure that we have 5 of cookie type A and 5 of cookie type B. All right, and then we could get 5 on the bottom shelf. We would put 5 A's and 5 B's. All right, that way you have the same number that are cooking. So a block design would take into account the location, which might affect the cooking. All right, so that would be a better design, because if the top shelf cooked faster than the bottom shelf, then these might be burnt, or vice versa. All right, so if you had more A's on the top, but they were burnt, people would probably like B more. So your location might affect your results. Well, here, all right, if you did it this way, you could make a comparison between the A's on the top shelf and the bottom shelf. You could make a comparison to the bottom shelf of B's, okay? Or you could look within the block itself. Okay, so like for 5 people are going to use, all right, here like one person is going to get an A and a B off the top shelf. And then they can make a comparison. Then location's not going to affect it. And then someone else is going to get an A cookie and a B cookie. And that's going to happen 5 times. And you could do the same thing down here. All right, that would probably be the best way to do it. That way you've blocked out for location. All right, someone's going to get an A and a B off the bottom shelf. And then when they make their comparison, they choose which one they like better. It's going to be easier to tell. All right. So the reason why the block works better, all right, a randomized block works better is because it takes location of the baking into account. All right, and here would be like my randomized block design, that outline. All right, so we're going to put 5A and 5B on each tray. And each taste tester will get an A and B cookie from the same tray. That's probably the best way to do it. All right, we'll do this activity in class, get your heart beating. But a common type of randomized block design for comparing two treatments is called a matched pairs design. All right, so basically what a matched pairs is, it can be one of several things. So say you have one person, all right, a person can act as their own control. All right, so maybe they take a test, take a pretest, then you do something to them, you give them some sort of information, then they take a post-test. Okay, so that's a matched pair because you're comparing what they did before and what they did after. Okay, so a lot of times a matched pair is like a before or after. Or maybe measuring something with their left hand and something with their right hand. Or a matched pair design can be that you compare two individuals that are alike in a lot of ways. And maybe you have John over here, and maybe you have Paul, and maybe both of them are 50 years old, or around 50 years old. They're both in good health. All right, maybe they're both married with 3 kids or something like that. But you give John a drug and you give Paul a placebo. And because they're alike in a lot of ways, maybe they're both about the same height, the same weight, the same age, then you're able to compare. That can also be a matched pair design. But these two people have to be very, very close. And it doesn't have to be people. I mean, we know individuals don't have to be people. They can be things. Okay, they can be things. They can be blocks of cheese. It doesn't really matter. All right, so that's what a matched pairs design is. All right, and in the last section, I'm just going to put it with this video here. Okay, using studies wisely. Let's read a few of these bullet points. We can call this chapter done. It says, most statistical studies aim to make inferences that go beyond the data that's actually produced. Inference, or making guesses about the population, requires that the individuals taking part in a study be randomly selected from the larger population. Okay. Now, if it's an experiment, you can't do experiments on people after you randomly select them. I mean, most of those experiments, people have to volunteer themselves. Okay, so if it's an experiment, you don't necessarily have random selection, but you do have random assignment. Okay. So in the case for experiments, a well-designed experiment that randomly assigns treatments to people or experimental units makes you able to draw cause and effect. Okay, so with experiments, you can use words like cause, but if it's not an experiment, you cannot use cause and effect. All right, if there's a lack of realism in an experiment, you can't generalize the results. All right. The next bullet says, in the absence of an experiment, so if it's an observational study, you really can't claim causation. All right, unless you repeat the observational studies many, many times and you get the same results, or you have consistent results in many studies. So, unless you have a lot of studies, if you do a single observational study, you cannot claim causation. You can claim correlation, but you cannot claim causation. If you're going to do experiments on people, then the experiment has to be screened in advance by some sort of institutional review board, and the people have got to give their consent. and you have to agree to keep the results confidential. You cannot share medical information from an experiment. All right. So the only times, or remember that randomized comparative experiments can answer questions that can't be answered without them. Also remember that the interests of the subject must always prevail over the interests of science and society. So if you think like smoking causes cancer, you cannot make one group smoke a bunch of tobacco and see if it causes cancer or not. The people's health is the most important thing, so you can't take that lightly. So if you're not sure if something, if you think something, a new drug might hurt somebody, the person's interest has to come above the drug interest. Okay, so it's erring on the side of caution. That's what this bullet says. If you're not sure about what the results are going to be, if you're not sure that some new thing might hurt somebody, you can't do it. If you think it could, then you shouldn't do the experiment. So those are the main bullets from 4.3, but it's still good reading just for your own knowledge. So hopefully that information helped, and we'll stop it there.